Welcome to the second lecture in week 9. This is lecture 9B. We're still in mechanical considerations and we're still dealing with steam. In this case, we're going to look at trying to get or make steam from a waste heat source. So earlier we looked at extracting high temperature exhaust to preheat combustion supply air. So that we looked at a number of lectures ago. Another use for high temperature waste is actually to produce steam. So in the previous example, we used this high temperature to actually preheat some sort of oil or something in a heat exchanger and preheat our combustion supply air. In this case, we're going to take that high temperature waste to produce steam. The high temperature exhaust is actually supplied to a burner area of a waste heat boiler where the burner assembly has been replaced, and that high temperature exhaust is actually going to create or make steam. Now dampers control the flow of exhaust gas into the boiler and thus the steam pressure. That's sort of the basic premise behind this. Now the first thing, care must be taken not to allow the exhaust gas to cool too low, where undesirables that are located in the exhaust, byproducts of combustion, are allowed to condensate, such as sulfur products and nitrogen products. Below is sort of a not to go below number for different steam pressures. So on low pressure steam, common steam pressures that we see in most businesses, we don't really want the exhaust gas to drop below 350. In sort of a medium pressure system, like up in the hundreds to 150, we don't want the exhaust gas to drop below 500. And then finally, high pressure systems, anything above 150 psig, I want to keep the exhaust gas temperature from dropping below 550. The savings equation, if we look at this by using this waste exhaust, the first thing I have here is the 1.08 because I'm dealing with a CFM situation or a convective heat transfer. And then there's a 0.027, and if we look below, the ratio 0.027 over 0.024 corrects for the higher specific heat of exhaust gases at this extremely elevated temperatures. So that 0.27 over 0.24 is actually a correction factor for the ultra high temperature. There's also one other correction factor, and that's calculating a standard CFM. And again, this is due to the high exhaust gas temperatures. The standard CFM of the exhaust gas, if we look down below, there's a formula on how to calculate that. Standard CFM is the measured CFM times, and then in brackets, we have 530 divided by the exhaust gas temp into the boiler plus 460. So that's all multiplied by the actual measured CFM of the exhaust gas. That gives me or standardizes the CFM. And again, those two parameters, the 0.27 over 0.24 and calculating a standard CFM, are correction factors needed because of the ultra high temperatures that we're dealing with the exhaust gas. Now, so I have my two correction factors, then I multiply my delta T, this is my delta T, and so now if we look at it, I have 1.08 times CFM times delta T times the hours of operation times the fuel unit heating cost divided by the fuel unit heating value and heating efficiency. So this equation should look very familiar to any convective type of calculation, with the exception again of the two correction factors because we're dealing with an ultra high temperature situation here. So I have an example. I have a furnace exhausting at 5,000 actual CFM of combustion products at 1400 degrees Fahrenheit. The exhaust gases are to be used to make 125 psig steam in place of steam from a gas-fired boiler. I'm going to be able to operate this situation about 2,000 hours per year at a cost of gas at $1.42 per CCF. In this case, 1 CCF is 100,000 BTUs, and the boiler efficiency is 76%. So step one in this is I have to get that standard CFM. I know what my actual CFM is, but I have to standardize it due to the high temperature, so I can use it in that equation, because the equation is based on the 1.08. Now, I take the 5,000 actual CFM, and again I take 530 degrees divided by the 1,400 degree temperature of my exhaust gas plus 460, and when I run this equation out I get 1425. That's my corrected or standard CFM. So when I plug that into the equation, I have the 1.08, which is typical in convective equations. I've corrected for the high temperature here and here. I have a delta T, I'm exhausting 1400, and I don't want to go below 500. That 500 is the not to go below number, so I don't start condensing undesirables out. My hours of operation per year at 2,000 times the cost of fuel. And again, this is my correction factor, the BTUs per the unit of fuel times my efficiency of my boiler. And I get a grand total of 58,228.88. Now, included in this steam section of your notes, the federal government put out a handy little steam efficiency for systems handbook. I think it's 100 and some pages. I did include this in your documentation. You can also go out on the internet and find the same document if you want to get it straight from the federal government. It's sort of a handy document to go through and look at some of the other things that the federal government has looked at as far as energy savings when it comes to steam systems. And that has everything to do from insulating steam pipes, you name it, but there's a lot more things that can be looked at under steam. I just wanted to give you two examples in here, but due to the short nature of the class during the summer, we don't really have the time to go into other issues. This ends the second lecture for week 9. You now can proceed to assessment 9. This ends the lectures of week 9. Thank you.